Ever spend like ages searching for something
Uh-huh.
only to find it was right under your nose the whole time?
Yeah.
It's kind of like that with optimizing complex problems,
Yeah.
you know?
I can see that.
But what if there was a way to search everywhere all at once?
Oh, wow.
That's kind of the idea behind quantum annealing.
It is, yeah. It's using quantum
All
mechanics
right.
to change how we solve really tough problems, potentially.
And that's what we're diving into today.
Yeah.
You sent us this paper
I did.
by Abel, Blance, and Spanowski.
Yeah, it's a good one.
And they basically took quantum annealing and put it head-to-head with
The classic.
the usual suspects, yeah.
Yeah.
Using a real D-Wave system, too, which is cool.
A real-life quantum annealer.
So cool.
It's not just theoretical anymore.
Exactly.
They wanted to see not just does it work, but how is it different than all the other ways we've been doing things.
And they start with this analogy
Oh, yeah.
of bumpy landscape.
That's a good one.
Every peak and valley is a different possible solution.
It's good visual, I get it.
Yeah.
But then they talk about
Wow.
quantum tunneling through the hills to find the lowest point.
Yeah.
And I gotta admit, for a second I thought they were pulling our leg.
It does sound kind of crazy, right?
It does.
But that's quantum mechanics for you.
Right.
It's like instead of a hiker trying to find the lowest point,
Yeah.
we've got this little quantum robot zipping around.
Okay.
And it can teleport. Short hops, but still right through those hills.
So instead of slowly going downhill, it's like instantly checking everywhere.
Exactly. It's not limited by those hills like we are.
No wonder those local minima, those valleys that aren't the lowest,
Right. They can be deceptive.
they don't fool a quantum annealer.
Not at all. And that's what makes quantum annealing so powerful.
Okay.
It's not just faster. It's a whole different way of solving these problems.
Okay. I think I'm starting to get it.
Yeah.
But they keep mentioning the Ising model.
Right.
Is that like just a physicsy term for our bumpy landscape?
It's connected. Okay.
Picture a grid. Okay.
Okay.
But instead of hills, it's covered in tiny magnets.
All right. I'm picturing it.
And each magnet can only point up or down.
Okay. I'm with you.
That's the Ising model, a simple way to look at complex systems.
So instead of hills and valleys, we've got these magnets flipping around.
Exactly.
But how does that help us solve real-world problems?
Yeah, it's all about energy.
Energy. Okay.
Every single way those magnets can be arranged
Yeah.
has a certain amount of energy tied to it.
So some arrangements are more stable than others.
Exactly. And the goal is to find the absolute lowest energy state.
So finding the ground state means finding that perfect arrangement.
Exactly. And here's where it gets really cool. The way we do that, that's where classical and quantum annealing diverge completely.
Okay, so our quantum robot is teleporting, but what's the classical approach doing?
Imagine instead of a teleporter,
Yeah.
we have a good old-fashioned shaker.
A shaker.
Yeah, like we're making a protein shake.
Okay, I'm laughing, but I'm with you.
Classical thermal annealing is all about shaking those magnets.
Okay.
And the temperature, that controls how hard we shake.
So we're just trying to jostle them around, hope they settle into a lower energy state.
Pretty much, yeah. More of a brute force method.
No teleporting shortcuts here.
Nope. And that's the problem.
What's that?
Just shaking harder doesn't guarantee you find the absolute best solution.
Ah, you could still get stuck in a valley that looks good but isn't the best.
Exactly. Whereas our quantum friend, with their teleportation...
They just zip right over?
Exactly.
Okay, I see the difference.
And the researchers, they tested this with a 2D Ising model.
So a flat grid of magnets.
Exactly. And the quantum annealer, it consistently found that ground state way faster, way more reliably than just shaking things up.
So it wasn't a fluke. It really is better at finding that optimal solution.
Absolutely.
But how do we go from magnets on a grid to, like, designing a new medicine?
It's a big leap, for sure.
It is.
But that's what's so cool about this paper.
That's like...
They didn't stop at magnets. They wanted to go further.
So how do you go from a simple grid to something as complex as a new drug?
They used a very clever technique.
Oh, what's that?
It's called domain wall encoding.
Domain wall encoding.
Yeah, it's like translating those real-world problems into the language of spins.
So giving the annealer a dictionary to understand these more complex problems.
Exactly. And to really test this translation,
Yeah.
they got really creative with the problems they threw at it.
Okay, so we're not talking simple anymore.
Oh, no.
They really wanted to see if this quantum annealer could handle the complicated stuff.
We're not talking hills anymore. Think more like, I don't know,
Yeah.
imagine a sheet of metal all crumpled up.
Okay.
That's kind of what this first function was like.
the corrugated landscape, right?
Yeah, peaks and valleys everywhere, totally chaotic.
Yeah, good luck finding the lowest point on that.
Exactly. That's the point. It would make normal computers cry.
And then it sounds like they just kept making it harder.
Oh, yeah, they were having fun with it.
The multi-well potential. What was that one like?
Picture a plateau, nice and flat, right?
Oh, I got it.
But then it's covered in holes, different depths.
So not only do you have to find a hole, you got to make sure it's the deepest one.
Exactly. Like a frustrating game of golf
Right.
where the ball keeps disappearing.
Okay, that would be rough.
And if that wasn't enough,
What?
there's more.
Oh, yeah, they saved the best for last.
Okay.
The volcano crater.
So, literally a volcano.
Steep sides, narrow crater at the bottom.
Okay, I get it. They weren't messing around.
Nope. They wanted to push the limits.
But why go through all that trouble? What's the point of these weird landscapes?
Because the real world is messy.
Sure enough.
Drug design, material science, it's not neat little grids.
So these functions, they're like mini versions of those real problems.
Exactly. Stress tests to see if quantum annealing can really handle it.
So if it can ace these impossible tests,
It shows it's got potential for the real deal.
like a marathon runner training in the mountains.
So what happened? Did the quantum annealer rise to the challenge?
Oh yeah, it crushed it.
Really?
All three functions, the quantum annealer consistently found that global minimum, that best solution.
No getting tricked by those fake-out values.
Well, meanwhile, the classical methods, they got stuck all the time.
So it wasn't just luck. The quantum annealer was fundamentally better.
It really seems that way. Like it had an intuition for finding the right answer.
That's kind of mind-blowing when you think about it.
It is. And it could mean that problems we thought were impossible
Yeah.
might actually be solvable with this technology.
Okay, so now I really want to know how they did it.
The domain wall encoding.
Yeah, that's the key, right? Okay, so let's break it down.
Break it down.
Domain well encoding, that's the magic phrase.
It's pretty clever.
How'd they actually use it to test those functions?
So they took each of those crazy landscapes, right?
Crumpled metal, the volcano, all of them.
Yep. And they basically turned them into a connect the dots for the annealer.
Connect the dots. Okay, I kind of see where you're going with this.
Each magnet, up or down, that's like a dot.
And by figuring out the right combination of ups and downs,
You find the lowest point in the original landscape. Exactly.
like a really, really complicated puzzle.
With a quantum twist. And here's the thing.
Yeah.
They didn't just try it once with the magnets in some random starting position.
Oh, so they mixed it up.
Multiple runs every time,
Yeah.
totally different random setup.
So it's like they were dropping that quantum robot onto the landscape blindfolded.
Pretty much. And to be fair, they did the same thing for the classical methods.
So same starting points for everybody. A fair race.
Exactly. Level playing field.
What happened?
Well, the classical methods, they did all right sometimes,
Sometimes.
but they got stuck a lot too, especially as the landscapes got more complex.
Those pesky local minima, they're like tourist traps for algorithms.
And the quantum annealer. Straight to the bottom, every single time, no detours.
Like it had a map the whole time. So we're not just talking faster, it's smarter.
It's fundamentally different. It can explore solutions in ways we can't even imagine.
So problems we thought were impossible could actually be within reach.
That's the exciting part. Designing new materials, personalized medicine, even AI.
It's like we've stumbled onto a whole new toolbox, and we're just figuring out how to use it.
We've got a lot to learn. Bigger annealers, more access for researcher.
But it's a good problem to have. To be on the edge of something this big, it's incredible.
It really is. And this paper, it's just the beginning. Who knows what we'll discover next?
That's the beauty of a deep dive, isn't it? You never know where it'll lead.
Exactly.
Well, on that note, huge thanks to you. This was fascinating.
Glad you enjoyed it.
And to everyone listening, keep those questions coming. Keep exploring. You never know. You might be the one to take this even further.